Alrighty, back for section 7.4. Today we're going to look at logarithms and what are some of the properties of logarithms that we can do to simplify them and make them a little bit easier to deal with. So our EQ is what characteristics do logarithms have that can help to simplify them. Look at that. So there's a quick little warm up. A new car loses 15% of its value each year. What will a $25,000 car be worth in 5 years? So we know that this car is going down in value, so we have a decay problem. $25,000 is going to be our start value, right? That's how much we're paying for the car straight away. I want to know what is the value in 5 years. So we're going to set up our equation, which if you recall is a start value times 1 minus in this case. Since I'm losing 15%, I do need to change that 15% into a decimal, which is 0.15. Again, I can achieve that either by dividing by 100 or moving the decimal over 2 spots. If I put 0.15 in here and I want to know the value in 5 years, so that's my time, which is also my exponent. Then I'm going to clean up the decay factor in the parentheses there. I'm going to simplify that to be 0.85 raised to the 5th power. And again, I should have a decay factor, or I should have a decay factor of less than 1 since I know that the value of this vehicle is going down. We type in the calculator, 0.85 raised to the 5th. So after 5 years, that car is only worth $11,092.63. Okay, so we have the end value, which is a pretty significant. It's lost over half of its value in 5 years, but that is pretty common. If you do end up buying a brand new car someday, they lose their value pretty quickly. So we saw in section 7.3 that logarithms are just the inverse of exponential functions. So there are 3 properties that we know with exponential functions, and I'm going to show you just like what the logarithmic version of the same thing is. So when we talked about exponentials, we knew that if I have a variable, like let's say x to the m power. So I'm going to give you an actual example here in a second. I'm going to do one just like in general with all variables. We know that if we're multiplying powers that have the same base, I can go ahead and add those powers together. Okay, so x to the m times x to the n, I could add them up. So an example of that would be 2 to the 3rd times 2 to the 4th would equal 2 to the 7th. Okay, that was one exponential property. And again, because the logs are just straight inverses, almost the same thing's true, but adding and multiplying are going to switch spots. So the logarithmic version, and the first property that we need to know, is that if I have log base b of m plus log base b of n, what I can do is combine those into a single logarithm by multiplying their arguments. Okay, so using numbers, a numeric example of this would be log base 2 of 8 plus log base 2 of 16 is equal to log base 2 of 128, and this number comes from 8 multiplied by 16. Okay, so with exponentials, if we're multiplying, we can add the powers. With logarithms, if we're adding, we can multiply the arguments. So similarities there, but it is the exact opposite in how we combine. So that's what we call the product property. Okay, so there's one. Number 2 is the quotient property. Almost the same thing. We know with exponents, it's x to the m divided by x to the n. I can go ahead and subtract those powers. So again, an example of that would be 3 to the 3rd divided by 3 to the first. That would be 3 to the second. And again, I get 3 squared because it's 3 minus 1. Okay. With logarithms, again, it's going to be the opposite, where if I'm subtracting logs, then I can divide. So it's got some similarities there. So if I have log base b of m minus log base b of n, that is equal to log base b of m divided by n. Okay, so I can condense two logarithms into a single log as long as they are adding or subtracting. Another example of this would be like log base 3 of 27 minus log base 3 of 3. I could then say is equal to log base 3 of 27 divided by 3, which of course is 9. Okay, so again, second property, if I am subtracting logs, then I can write their arguments as a fraction of a single logarithm. Okay, so when adding logs, you multiply the arguments together. When I'm subtracting logs, I divide the arguments. And finally, the last property that we have is called the power property. Just like with exponents, it was if I have a power that's raised to another power, then I can multiply these together. Okay, so if I had like 2 to the third raised to the fifth, that was equal to 2 to the 15th power. Okay, so I could just multiply the 3 and the 5 together. With logarithms, it's not quite an exact analog of it, but what can happen with powers if you have a log, so let's say it was the log base b of x to the m power. Okay, so if you have an exponent inside your logarithm, what you can do is you can bring the exponent out front and write it as a multiplication problem. So log base b of x to the m power can be rewritten as m times log base b of just x. Okay, so what happens is I took that power, I took this power and I brought it out front. Okay, so for example, let's say you had log base 4 of, let's just use x again, x to the 7th power. Okay, you could rewrite that as 7 times log base 4 of x. Okay, and the reverse is true. If you have 3 times log base 5 of t, that could be rewritten. You could take that and move it up to the exponent of t and write it as log base 5 of t cubed. Okay, now all of these different properties will be useful at different times, but those are the big three that we need to know. If you're adding, you can multiply the arguments. If you're subtracting, you can divide the arguments. And if your argument has a power, it can be brought out front and written as a coefficient. Okay, so we can use the properties of logarithms to simplify the sum or difference. Okay, but with logs, we have to see that plus or minus sign. They also have to have the same base. We'll talk about what happens if they don't have the same base a little bit later. So if I see log base 3 of 54 minus log base 3 of 2, okay, again, because it's subtraction, I can write this as a single logarithm of 54 divided by 2. Okay, that can be rewritten as log base 3 of 27. And then anytime you have a logarithm, if you can evaluate it, we want to. Remember, when you see a log, what you should be thinking is the base number raised to what power equals 27. Okay, so the base number raised to what power gives me the argument, and in this case, we know 3 to the 3rd power is equal to 27. So this is equal to 3. Okay, So if you are simplifying square roots, combine them together like we did here. Okay, so this was kind of phase one to get to this, but then we want to see, can I evaluate that logarithm? And indeed, that does just equal 3. Okay. So we have 3 logarithms like this. What I'm first going to do, anytime you're condensing this down, you want to get rid of coefficients and put them up as powers right away. So I'm going to rewrite this as log 5 plus log of 2 squared plus log of 50. Okay. So this becomes a 2 squared is 4, right? So if I just look at combining these first 2 logarithms, you could combine all 3 at the same time right now. I'm just going to go 2 at a time. So this would be log of 5 times 4, okay, which should be 20. Okay, so this would be log 20 plus log of 50. Now again, because it's addition, I can multiply the arguments together. So I can multiply 20 times 50 and get log of 1,000. Okay, so I've condensed those 3 logarithms into one, and now I want to see, can I evaluate this? Is this equal to a single number? If it's a whole number, great. If not, I'm going to leave it like that. But remember, if you're missing a base in a logarithm, it's base 10. And 10 again to the 3rd power is equal to 1,000. So log base 10 of 1,000 is equal to 3. And this is actually something you could plug into the calculator. Okay, just to show you again on the calculator, the log button's on the left side there. If I type in log of 1,000, I should just get 3. Okay, so if it's addition or subtraction, okay, we can combine logarithms together using those 3 properties. Go ahead and give these 2 a shot. Okay, simplify what you can, and we'll go from there. So all of these are base 4, so I know I'm good to go to combine all these right away. Here, these first 2 are adding, so I'm going to multiply. That would be log base 4 of 160, because 8 times 20 is 160. Then I have to subtract log base 4 of 10. Because it's subtraction, I'm going to go ahead and divide the arguments now. So this will be log base 4 of 160 divided by 10. Okay, which of course is 16. So log base 4 of 16, which is just equal to 2, because 4 squared gives me 16. So this whole thing I could say is equal to 2. Okay. Here, again, I'm working in base 10, and I know that because I don't see a small base number. I do want to go ahead and get rid of this 2 right away, so I'm going to ship that up to the top. So I got log 7. Actually, you know what? I'm going to do 2 things at once. I'm going to move the 2 up to the power of 3, but I'm also going to combine these 2 logs together. So 7 times x, I can't do anything with, so I'll just call that 7x minus log of what has now become 9. I know it's 9 because this became 3 to the 2nd power. It's subtraction in between these logarithms, so that tells me I'm going to have a fraction inside my log. So this would be 7x over 9. I can't simplify anything with that, so this would actually be my finalized simplified answer. So 2 here. This I couldn't evaluate because of that variable, but that's how we can kind of take multiple logarithms and condense it down into one. The flip side of that is expanding logs. Sometimes it's useful to take a logarithm that's got a bunch of stuff going on inside the argument and to split it up. So if I look at this, this is telling me I want to take log base 5 of 25 times x squared. So I'm going to split this up into log base 5 of 25 and log base 5 of x squared. Okay, because it was multiplication there, I'm going to go ahead and put a plus sign in the middle. Okay, I know it has to be addition because the 25 and the x squared were multiplied. And then all I'm going to do here is I notice here that log base 5 of 25 is just equal to the number 2 because 5 squared gives me 25. And then when you're expanding, and this is kind of tricky to remember, just like when we were condensing, we wanted to take coefficients and put them into powers, right? That's what we did right back here. This 2 right here became an exponent, okay? When we are expanding, if you see that word expand, you are going to bring exponents down out front. So I would have 2 plus 2 log base 5 then of just x, okay? I can't combine those together because one's just the number 2 and one is 2 times the logarithm. So this is my final simplified answer here. Okay. So that was that first one. Okay. If I see this log, so there's 3 things going on in this problem, right? I have 10 times x, but then it's 729 on the bottom. So that means I need log base 9 of 10. I need log base 9 of x. And I need log base 9 of 729. Okay, because the 10 and the x, it's basically anything in the numerator will be a positive logarithm. So since 10 and x are in the numerator of the original, I'm going to add these together. Okay, and because 729 was in the bottom, I'm going to subtract that one. This is something that you would just try typing in the calculator, but this log actually can be simplified because 9 to the 3rd power is 729, which means I can end that with just minus 3. So my final answer here, my expansion, would be log base 9 of 10 plus log base 9 of x, and then minus 3 on the outside there. It is important to be able to do both of these. More often you will be condensing logarithms. It's not too often that we'll use the expansion, but it's still important to know because from time to time we will need to be able to do it. Okay, so 3 properties: condensing, expanding. So the last thing here, go ahead and give these 2 a shot, and then we'll wrap up with the change of base formula. So log base 3 of 9x. Okay, I see in here it's 9 times x. So I'm going to do log base 3 of 9 plus log base 3 of x. 3 to the 2nd power is 9, so this first log is just 2, plus log base 3 of my variable. Can't do anything with that, so there's that one. Okay, and then log base 7. You should hopefully, you should immediately see the tie between 7 and 49 and know that you will simplify that later, but we first need to break it apart, and that's why we want to be able to expand. So I should have log base 7 of 49 plus log base 7 of x squared, and then minus, since 10 is in the denominator, minus log base 7 of 10. Whew. So a couple things to do here. This log base 7 of 49, that thing is just equal to 2 because 7 squared is 49. Log base 7 of x squared, I can't simplify into just a simple number, but I am going to take that power and bring it out front. So this is 2 times log base 7 of x. And then 10 and 7 have nothing in common, so I'm just going to keep that alone. Okay. So here is our final expansion. Now, this last part is actually maybe the most important formula when it comes to logarithms. Reason being that most calculators only have a button for, right, if you look at the calculator here, I only have a log button, and that's only base 10. And a lot of times it can be tricky to type in logarithms with separate bases. Some calculators do have the ability to do it, but a quick and easy way to do this is so if I want to type in log base 4 of 15 into the calculator, I'm going to use just the regular log button, and I'm going to do log of the argument, which in this case is 15, and divide by the log of my base number. Now notice that I changed the base, right? And that's why it's called the change of base formula. I went from base 4 to now in my calculator, I'm doing base 10, which is something that my machine can do. Okay, and every machine can do logarithms. So I'm going to type in log 15, divided by log 4. Make sure you close those parentheses after the 15. Okay, and that gives me 1.95. And what that tells me is that 4 raised to that power, 195,344,5298, should give me exactly 15. Okay, so if you are trying to figure out log base 4 of 15, in the calculator you can simply type log 15 divided by log 4, and we get approximately 1.95. Okay, it's pretty powerful stuff that because now that opens up any base. So if you want to type any base into the calculator, it doesn't have to be base 10. We can do it. So this, if you think of what log base 2 of 47 is asking, it's saying 2 to what power gives me 47. So I'm going to do that, I'm just going to use base 10 and go log 47 over log of 2. Okay. In the calculator, log of 47 divided by log of 2. It's 5.55. So if I raise 2 to that power, I should get 47. And sure enough, I get 47 there. So log base 2 of 47 is approximately 5.55. I think that's what it was. Doesn't matter. It's close. 5.55. Yep. So that's just kind of a quick rundown. Those are the three main properties that we're going to use from earlier. And this change of base formula allows us to use any machine to calculate logarithms. If you really care, there's a proof. Most of you probably don't care. Homework 7.4, 466. See you next time. Come on. Okay, bye.